So what we want to look at then is the use of logarithms. So that's the basic thing we need to look at to solve what's called an indicial equation. So what are logarithms? Well, the logarithm to the base 10 of a number is the power to which I have to raise 10 to get that number. Logarithm is a power, in other words. So what is a logarithm? It's a power. Power of 10 usually. Because we tend to work in tens, the decimal system is one we're very familiar with. Base 10 is often used with logarithms, and it's the power to which I have to raise 10 to get a number. For example, if we look at it, we can think of the logarithm as like an indicial, an inverse function rather. So if I have an equation like this to solve, 10 raised to some power x is 36. What is x? This is an example of an indicial equation. So you remember we said at the beginning of today, an indicial equation is one where the unknown is in the power. Well, here's an example. And looking at that, it's quite awkward to think, how can I work out what x is? I'd have to just try it on the calculator. 10 to the power, try all different numbers until I end up with 36. But there is a way to do it. Logarithms are a bit like the inverse of to the power. So if 10 to the power x is 36, then we say the logarithm to the base 10 of 36 is x. And you've got that button on your calculator. Logarithm to the base 10 is used so often that we often leave the 10 off. So logarithm on its own means to the base 10. And if you look at your calculator, you'll see log button. So if you hit log 36, you get so the logarithm to the base 10 of 36, or log of 36, from the calculator is 1.556. 4 significant figures. And because it's a power of 10, we need accuracy. So 3, 4 significant figures is common. What that's telling us is that now 10, therefore 10 to the base 1.556, sorry, 10 raised to the power 1.556 should be 36. And if you put that into the calculator, you get, right, so near enough, okay? And it's not quite there because of the rounding that's going on in the 1.556. So we do round to a reasonable accuracy to make sure we get the answer. So how do I solve an equation like 10 to the power x is 36? I find the logarithm of 36, and that tells me the answer. So that's what logarithms are. They're powers, usually to the base 10. We'll be using base 10 for most of the time during this part of the course. Later on we'll come across another base, which is the natural number e, and we'll end up with a natural logarithm that you might have come across already in other units. And we use them to solve equations where the unknown is in the power. The indicial equation then, as we were saying earlier, 10 to the x equals 36 is an example of an indicial equation because it involves the power. X is either in the base, it's the base in other words, we've got to find out what that base is, or it's in the index, the power. We've got an indicial equation and we use logarithms to solve it, generally logarithms to the base 10. We then have some rules of logarithms that help us to use logs. Okay? Logarithms are powers. And we've got the laws of indices written down. We looked at the drill beginning of today. Some base x squared times x cubed, we add the powers. If the base is the same, we can add the powers when we multiply them together. The same thing is true for logarithms. The logarithm means, by definition, that the base is the same. It's base 10. doesn't like the 0, base 10, okay? So I've got two numbers multiplied together and I find the logarithm. It's the same as the addition. I add them. Dividing two numbers and then finding the logarithm, I subtract them because they're powers now. This one's the one that we're going to find the most useful. The logarithm of a number raised to some power, that power comes down and becomes a multiplier, like that third law of indices that we're looking at. And then finally, something that's worth remembering, the log of 0. Anything to the power 0, remember, is 1, so the logarithm of 0 is 1. So these are the laws of logarithms, and you might want to just jot down what they are. So, but again, you've got these notes, you can print them out off the site. And we'll look at this in more detail next week. But what I want to do now is just look at some examples of how they can be used to solve indicial equations, just to introduce them to you. Let's look at this, okay? Try and solve this. Do you remember earlier on today we were talking about we can do anything we like to an equation so long as we do the same thing to both sides? Right, I want to solve this. We can do anything we like to one side of the equation so long as we do to the other, as we were talking about earlier. So logarithms, taking the logarithms of both sides is equally valid. What I do is I find the logarithm of this number, 2 to the x, equals the logarithm, and I'll just put it in a different colour to emphasize it, of 12. Because this is the logarithm of 2, this is like the log of 2 is like a power. Remember, the logarithm is a power raised to another power. From the law of indices, or the laws of logs that we were looking at on the previous slide, here, if I've got a logarithm raised to a power, I can bring the power down and turn it into a multiplier. So that's what I do here. I bring the x down and put it in front. And that's where these become useful. X. Okay, so x times the logarithm of 2, so bringing that x down and turning it into a multiply is the real power of these logarithms, equals the logarithm of 12. Remember, these are numbers. We've already done one on the calculator. You could key log 12 into a calculator, it's a number, and so is the logarithm of 2. So I can divide both sides by that number. I want to get rid of this bit, the log 2 bit, so divide by it. X equals the log of 12 divided by the log of 2. And I've solved this equation, this indicial equation. And in the calculator I can calculate that. What is the log of 12 divided by the log of 2? So x equals 3.585 to 4 significant figures. Let's just look at this again and see the steps. There's the equation to solve. So the first step, because the unknown is in the power, or it's to do with powers anyway, I take the logarithm of both sides there, which means that this x can come down and become multiplied. So I brought this x down here, and that's the key step. That means now this number has been times by the x, so I can divide both sides by that number, log 2, and we get x equals log 12 divided by log 2, which is 3.585. How can I check that that's right? Yeah, back in here, 2 to the power, whatever that number is, should be 12. So as a final thing, just do that on the calculator. What is that? Right, so 2 to the power x, 3.585 equals, sorry, 0.0003. So near enough, okay? And again, just down to rounding. So we can find powers using the laws of logarithms, okay? So one more example, 4 to the power x plus 2 equals 13.8. So the unknown is in the power. What's the first thing we do? So we find the logarithm of both sides, which means the x plus 2 comes down and multiplies. That's always the case. So we can miss out an intermediate step and just write, therefore, x plus 2, which is the power, multiplied by the logarithm of 4 equals the logarithm of 13.8. So that's the first step, and that's generally what we do when we solve indicial equations. We take the logarithm of both sides, which means that whatever the power is, it comes down and multiplies. Now remember, this is a number, so divide by it. Divide both sides by the log of 4. You could expand out this bracket, but this is quite an awkward number, so x times that number plus 2 times that number, you're making it more complicated. So as in the equations we were looking at earlier, divide both sides by log 4 is probably the easiest thing to do. So x plus 2, don't need the brackets anymore, equals the log of 13.8 divided by the log of 4. So it's now just like equations. We do one thing to one side, do it to the other. This looks awkward, but remember, it's only a number. You could put it into your calculator and find out what that number was if you wanted. Now, finally, x has had 2 added, so subtract 2 from both sides. X equals log 13.8 over log 4 minus 2. And then we get the calculator out and work it out. X is negative 0.1067. We can have negative powers. We mean remember, negative powers mean the inverse, so that's a number smaller than 1 effectively. Okay, you could now have a look at some of the exercise questions on that, the work in the Maths at Lowestoft College site, and then maybe even look at the questions in the assignment 1. Okay, and next week we'll pick up on this again.